Hi, you guys. So I'm back with the worked out examples from the mole lecture notes. And so I'm using a little bit of a different format so that I can emphasize some things. But first I want to look at this problem using lithium and the molar mass of lithium. This first question says, how many moles are in 21 grams of lithium? And since 21 is our starting value, I just went ahead and plugged it in right there. So there's my starting value, and my unit conversion that I need to use is that 7 grams of lithium is 1 mole of lithium. So I've got my 7 grams on the bottom so that my grams cancel out, and my mole is on top. My problem is asking me for moles, so it's a really good sign that I'm ending in the unit that I'm looking for. So that's handy. Now I just need to do 21 times 1 divided by 7, which gives me an answer of 3 moles of lithium. This conversion factor that we have right here, that is the molar mass. I'm really bad at writing on this touchscreen thingy, but hopefully I'll become more coordinated. Next question is saying how many atoms of lithium are in 14 grams of lithium? So starting point, oh geez, okay, nope, don't want that. Okay, starting point is 14 grams of lithium. And so we're gonna plug that in at the beginning of our factor label line. And it's ultimately asking me to get 2 atoms. And for me, I think it's really important to go through the mole to get there. And so since that mole is really in the middle of my conversion factor, I'm just going to go grams to moles and then moles to atoms because they're really individual relationships. So I'm going to use my molar mass. 7 grams of lithium is a mole of lithium. I put my grams on the top for my starting value, and then 7 grams on the bottom, so that cancels out. Now I'm in moles, but I really want to be in atoms. So now I have to use my other conversion factor, which is 1 mole of lithium is Avogadro's number worth of atoms, so 6.022 times 10 to the 23rd atoms. My moles cancel out, being on the top and the bottom. I am left with atoms, which is great since that was my target that I was looking for. Multiply the top, divide by the bottom. I get 1.2044, technical difficulties. 1.2044 times 10 to the 24th atoms of lithium. I somehow closed out of the thingy. I don't know. Whatever. Anyway, number 3, what is the mass, so that'll be grams, of 2.408 times 10 to the 24 atoms of lithium? So I'm like, all right, my atoms are my starting point. I'm going to plug those in over here. And then I want to go from atoms to moles so that I can eventually get to grams. So I'll put my atoms on the bottom so that they cancel out the atoms on the top. That gets me to moles of lithium. Then I can use my molar mass. 7 grams of lithium is 1 mole of lithium. My moles cancel out, and I'm left with grams, which is the unit I was looking for. So that's really good. And then multiply the top, divide by the bottom. Like usual, we end up with 27.99 moles of lithium, basically 28 moles, yeah. Wait a second. That should say grams. That makes way more sense. I was like, that's a lot of moles. Okay, that's grams, you guys. It really just, it wouldn't be a presentation for me if there wasn't at least like 7 things wrong with it. Okay, anywho, so you should be getting 27.99 grams of lithium. That looked like that. There. Grams. Okay. So then moving on to this next section, calculating the number of atoms. So we're going to diversify a little bit. So a silicon chip used in an integrated circuit of a cell phone has a mass of 9.63 times 10 to the negative 3 grams of silicon. How many silicon atoms are present? Okay, so I'm starting off in grams. I'm just going to make myself a little plan. I'm going to be in grams. Wow, that's sensationally bad. And I'm going to go to moles, and then I'm going to go to atoms. And if I want to get from grams to moles, I'm going to have to use that molar mass. That just looks like a normal M. I want a fancy M. Oh my gosh, you guys, this is ridiculous. Okay, anyway, we're going to use molar mass, and then over here, we can use Avogadro's number. Why? What is? Okay, anyway. So grams to moles to atoms. Start with my starting point, which is grams of silicon. Take that guy, plug it in over here. Then we are able to get the molar mass from the periodic table. So there's our molar mass. We put the mass, the grams, 28.9, on the bottom because we want these grams to cancel out. Then now we got to go from our moles to atoms. So I'm using Avogadro's number. So I have a mole of silicon is 1 mole of silicon, which is equal to Avogadro's number. So my moles cancel out. I'm left with atoms. Excellent. Multiply the top, divide by the bottom. Remember, when you're multiplying these numbers with scientific notation, it's best practice to put them in parentheses. Usually your calculator can figure it out anyway, but not always. So I just put it in parentheses to be on the safe side. We have 2.06 times 10 to the 20 atoms of silicon. And at the end of problems like this, I like to pause and think about, like, is this a reasonable number? And if we think about how tiny atoms are, yes, this is a reasonable number, right? We would have a lot of atoms in even the teeniest little silicon microchip because atoms are so small. Okay, so that's a good answer. That makes sense to us. Calculating number of moles and mass. A sample contains 7.03 times 10 to the 21 atoms of potassium. Calculate the number of moles in the sample and the mass of the sample. So the first thing I want to do is go from atoms to the mole, and then I can go from the mole to grams. So I'm going to need Avogadro's number, and then I'm going to need molar mass. Start with my starting point, 7.03 times 10 to the 21 atoms of potassium. Next, I'm using Avogadro's number to get the number of moles. So my atoms cancel and my atoms cancel. And I didn't write it on the slide, so I'm just going to work it out really quick. But you should get you should get 0.12 moles of potassium. Okay, and then this final step, we're using our molar mass from your best friend, the periodic table. 1 mole of potassium is equal to 39.1 grams of potassium. My moles cancel out. I'm left with grams. That's good. So we don't know the mass of the sample. And so then I can do my top multiplied together divided by the bottom. And we end up with 0.46 grams of potassium. Last but not least, we've got our diamond. And and we want to find the number of atoms. So diamond is a naturally occurring form of pure carbon. So we're just assuming there's only carbon in there. How many atoms are in a 1.75 carat diamond? And 1 carat is equal to 0.200 grams. So just looking at this real quick, we're going to have to go from carats to mass. So that's kind of mass to mass, but we're going from mass in carats to mass in grams. Then we can go to moles, and then we can go to atoms. So we'll use molar mass here, we'll use Avogadro's number here, and then for the carat to mass step, we can use the conversion factor that's provided by the question. So we'll start out with 1.75 carat diamond, and we want the carats to cancel out, so we'll put 1 carat on the bottom and our 0.200 grams of carbon on top. So carats are gone. Now we have 0.200 grams of carbon. We want to get to moles, so we have the molar mass of carbon from the periodic table. So that's our molar mass being used right there. And so the grams cancel out, so 12 goes on the bottom, 1 mole of carbon on the top. Then we're busting out Avogadro's number. We want moles to cancel, so we put that on the bottom, put Avogadro's number up top. In terms of atoms, we're left with atoms. That's what it's asking us about. Multiply the top, divide by the bottom. 1.75 times 10 to the 22 atoms of carbon. So there's a lot of atoms of carbon in one little diamond. And that makes sense. Makes sense that there would be a lot. All right, you guys, thanks for bearing with me through my many technical struggles here. I'm still figuring out how to use some of the features of my touchscreen foldy laptop and this very cheap stylus. So anyway, theoretically, I will improve and be less annoying. But we'll see. Okay, bye.